Okay, so in this video we're going to take a look at integration of fractions using the method of partial fractions. So first off, it's important to understand the difference between proper fractions and improper fractions. So in a proper fraction, the degree of the numerator is always lower than the degree of the denominator. So for example, if we have x to the nth power in the denominator, then in our numerator we must have a degree of less than n. However, in an improper fraction, the degree of the numerator is not lower than the degree of the denominator. So if we had x to the nth power in the denominator here, our numerator of an improper fraction would be greater than or equal to n. And in this video we're going to be focusing on proper fractions. So now let's take a look at what it's meant by partial fractions. So what partial fractions do are they take a fraction which can't be integrated directly and split it up using some simple algebra to something we can handle easier. So for example, if we were given this fraction, x divided by 2 minus x times x plus 3, it would be quite difficult for us to integrate it directly. So what partial fractions does is it takes this fraction and transforms it into two separate fractions. So we would have, for example, a over 2 minus x plus b over x plus 3, where a and b are unknown coefficients at this stage. So what we've done is we've separated this out into two separate parts, indicated in yellow and green here. Another example of how partial fractions can simplify fractions could be if we had 7 divided by x times x squared plus 1. Partial fractions would simplify this into a over x. And now, since we have a denominator with an x squared term and we're looking at proper fractions, we need to look at every possible degree of the numerator which is lower than x squared, so we need to take into account x to the first power and x to the 0th power. So we would have to have bx plus c, because this is the same thing as c times x to the 0 and a times x to the 0 here, divided by still our x squared plus 1 term here. And the same is true of all degrees of the numerator as well. So if we had a third example of 1 over x times x to the 4th power plus 3, partial fractions would reduce this again into a over x, which is the first part, plus, and now since we have x to the 4th power in the bottom, we need to account for the cubic term, the squared term, x to the 1st power, and x to the 0th power. Again, all divided by the second part of this fraction. So let's take a look at our first example. So in this example we're asked to find the integral of x divided by 2 minus x times x plus 3 with respect to x. So firstly, we know we're dealing with a proper fraction here, because when you multiply this out you end up with an x squared term which is less than an x to the 1st power up here. So now let's use partial fractions to simplify the integrand. So as we saw earlier, we now have that x over 2 minus x times x plus 3 is equal to some unknown constant a divided by 2 minus x plus some unknown constant b plus 3. So for us to simplify this further, we need to times both sides of this equation by the denominator given here. And then when we multiply this out, we'll find that this 2 minus x value here will cancel with this one, so we'll be left with an a times x plus 3. And then this x plus 3 value will cancel with this one, so we'll be left with a b times 2 minus x. So as you can see, this will cancel with this, and this will cancel with this. And then we're left with a much simpler expression. So therefore, x is equal to a times x plus 3 plus b times 2 minus x. So now all we need to do is work out what our coefficients a and b are. There are two different algebraic methods we can use here. The first is that we can choose any value of x in order to try and eliminate either a or b. Or the second method is coefficient analysis. However, we can already see that if we used coefficient analysis, every term has an x to the first in it. So we'd be left with 1 when we're evaluating x to the first power. However, we can see by choosing sensible values of x, we'd be able to eliminate either a or b and then solve for the other one. So from this logic, we're going to use method 1 in this example. So we can see here that if we choose the value of x equals 2, this will eliminate our b and it will keep our a. So let's go ahead and do that. So substituting x equals 2 in this expression gives us 2 is equal to a 2 plus 3 plus b 2 minus 2. And we can see straight away that this will cancel to 0, and this is 5. So this gives us that 2 is equal to 5a, therefore a is equal to 2/5. And now that we only have one unknown coefficient, we can choose any other value in order to give us our b. So if we choose x equals 0 for convenience, this gives us 0 equals 3a plus 2b, and we know already that our a is equal to 2/5, so that gives us 0 is equal to 6/5 plus 2b. Therefore, our b value must be equal to minus 3/5. So now we can go ahead and substitute our a and b values back into our original expression. And when you do that, you're left with this, where this is a and this is b. So from our previous video, which was the calculus 03.4, we know that the integral of the first derivative of some function divided by that function with respect to x is equal to the natural log of that function plus our constant of integration as always. Another option here is to use integration by substitution, which we saw in video calculus 03.2. However, you'll arrive at the same solution. So we can see here for this first part, we almost have exactly here. However, the derivative of minus x is minus 1. So what we need to do is add in a minus sign. And now we can directly apply our natural log method. So we have this is equal to minus 2/5 times the natural log of our 2 minus x denominator, and likewise the derivative of x plus 3 is just 1, which is what we have on the top here. This can be thought of as 1 multiplied by dx, So again, we can apply directly our natural log method. So we have minus 3/5 of the natural log of x plus 3. And as always, our constant of integration from this being an indefinite integral. So by using partial fractions, we were able to take a more difficult example, split it up into two smaller parts, and then integrate it almost directly. So in the next video, we're going to look at another example of partial fractions where we solve the integral, where the denominator has a higher degree of x to the first power. I'll see you there.